Well, hello and welcome, Nord Anglia, and thank you for joining us today for our MIT abstract on engineering with ecosystems with MIT architecture graduate student James Brice. I'm your host, Fatima Hussein, and I'm a PhD student here at MIT studying ancient Earth. Now, before we begin, I'd like to cue our listeners into what an abstract actually is. An abstract is just simply a snapshot or a summary of a greater work of research or writing. And with this series, we're bringing abstracts of inspiring MIT experts straight to you. Now, I'd like to welcome James today for his MIT abstract on engineering with ecosystems. James, I am so excited to talk to you. Take it away.
Hi, everyone. Thanks so much for joining. I'm really excited to talk to you guys today about some of the stuff that I've been working on. So, like the title, I'm going to be talking about some of the ways that we can think about our ecosystems differently, engineering with these ecosystems. So at MIT, I've been interested in exploring how research at the intersection of design, engineering, and ecological conservation can strengthen our coastlines against the negative impacts of climate change. So it's a little bit of a mouthful, but I'm going to break it down. Specifically, there are three important pieces there: design, engineering, and ecology. And I think it'll make a lot more sense if I talk to you a little bit about my background. But first, let's talk about the why. So why protect coastal ecosystems? What's going on there? It's actually a lot. Like I mentioned, the global climate is changing. So as our atmosphere warms due to greenhouse gas emissions, our oceans are warming up as well. That means higher sea levels, and our ocean is warming up. Higher sea levels mean more floods, and higher atmospheric temperatures mean more storms, which can be very dangerous for people living near the ocean. That's actually over 40% of the world's coastline. But it's not all related to climate change, actually. A lot of our coastal habitats are degrading because of human development too. You know, when we build our cities, our beaches, sometimes we take over the homes of the creatures living there. So remember, you know, when we're talking about coastal ecosystems or coastal communities, we're kind of thinking about those two things together. So it's not humans versus animals, but actually our coastal communities include the animals and our coastal ecosystems include the humans. So that's like an important part of that. So just like remember that kind of as I'm going on. So again, like I said, a little bit about my background. I'm from New York City originally. So big city, lots of people, lots of buildings, not typically a place you associate with nature or with wildlife, but there's actually a lot more wildlife in the city than people think. Some of the wildlife looks like this. So, you know, these are animals that have learned to live with humans in densely populated areas, some for thousands of years. We don't have rhesus monkeys in New York, but some cities do. All over the world, so we have different types of wildlife that live in cities. So different ecosystems, different animals. So the ecosystem that I'm going to talk specifically to you guys about more is this one. So this is a salt marsh. They're very common on the East Coast of the United States, and we have them in New York. Something that makes them unique actually is that they're what's called brackish. So that's essentially that they're freshwater and saltwater ecosystems. Salty from their proximity to the ocean, and fresh from the rivers or groundwater that feed into them. So I grew up around these salt marshes and I fell in love with them. I always liked the kinds of birds that live here. This is a marsh sparrow, that's an egret. But then I also really love the sea creatures, you know, the crabs, the clams, and the baby fish. So much so that I actually became a zookeeper. So my job at the zoo involved a lot of different things, and I got the chance to work with a lot of really amazing animals. I worked in education a little bit, so I went to schools and gave presentations about the animals, and then I also did some conservation work. So this is actually in the bottom right is from a horseshoe crab tagging exercise. I don't have a ton of time to talk about horseshoe crabs, but I really encourage you guys to look up more about them later because they're super cool. But you know, a lot of it is what people typically think about when they think about zookeeping. So it was taking care of the animals, what we call animal husbandry. that requires learning a lot about each species and the kind of environment that they live in. So if they like to climb, do they have things to climb on? If they like to dig, do they have things to dig in? Or, on the right here, we have our meerkats. They're big burrowers. So we gave them lots of little burrows. And so that was kind of like what got me thinking about environmental design. Towards the ending of my time at the zoo, I got to work as an aquarist with our aquatic collection. So fish don't breathe the air that we do, right? They breathe oxygen, but through the water by passing the water over their gills. So when I became an aquarist, I had a whole different set of questions I had to ask myself when taking care of the animals. Is the water the right temperature? Is it clean? Does it have the right set of nutrients in it? Calcium, nitrogen. And I also had to learn a lot about the life support. So, the pumps and the filters that we use to take care of these aquatic systems. And so in that way, I kind of got more interested in not just the animals living in the water, but the water itself as a physical thing. How does water move? How does it behave? And it turns out that question, even though it sounds sort of simple, is actually one of the hardest questions to answer in modern science. How does water move? So that brings me to my second piece, which is applied physics. And so this is the one that usually throws people off a little bit, but I studied physics in my undergraduate degree. So I got my bachelor's in applied physics because in addition to loving animals and nature growing up, I was very fascinated with how physical processes in the universe work as well. I really liked math. And so I wanted to know the answer to these questions. What is light? What is heat? Why does the wind blow? Why do stars form? Physics explains so much about the world around us, but even to this day, even though, we could fit a really powerful computer just like on the tip of your finger, we still don't know so much. And apparently one of those things is how water moves. So, we can come pretty close. I could show you really quickly, just so you guys kind of like get in this is like one of those, put yourself to sleep videos. But I think it's important to see this because, when we think about water, it gets very complicated very quickly, especially from a mathematical perspective. And so this equation on the right is called the Navier-Stokes equation. And it doesn't look too bad. It's just one line with some, weird little symbols in it. But it actually, like I said, is one of the hardest equations to solve in modern science. In fact, to this day, no one has solved it in its entirety. There's like $1 million prize for the first person that solves it. So anyway, I wanted to have this video here because, when you look at this and you look at the waves and all that foam, you can see how complicated it is. We call that turbulence. So it's messy and it's energetic. So, very hard problem in science. So anyway, what does this have to do with animals, right? I'll get there. But remember, we started this talking about climate change. I think I have to stop this before I move on. Okay, so flooding, storms. Even though it's hard for us to know exactly how water works, how a wave is coming, how big is it's going to be, we have a lot of ways to protect our shorelines already. And a lot of the time we build things like this. So on the right, this is what we call the seawall. And they work to a certain degree. I mean, they do stop the water. It's a pretty simple machine. But on the other hand, scientists have found out that these seawalls are actually not good for the environment, especially for ecosystems that rely on land and water. So remember, we were talking about the salt marsh. We can't have salt marshes if we block off the ocean because salt marshes are brackish. So they need that access to both the ocean on one side and to a freshwater source on the other side. And furthermore, it separates us from the land as humans, which, arguably is how we got in this issue in the first place. And so there are a lot of human communities as well that rely on access to the ocean, like fishing communities, for example. So what do? It turns out the solution to a lot of these problems is actually this. Nature has the answer. Now, I bet you're like, why is James showing me another picture of a salt marsh? But that's because the salt marsh is often the solution to these problems. So this is a gift from a lab at MIT. It's called the Neff Lab, run by Dr. Heidi Neff. I've been doing some collaboration with them. Here, they've modeled grasses in a flume, which is kind of like a wave tank. So it's a big tank and you have a machine that kind of moves the water artificially. And so they've modeled this here as a way to show how this aquatic vegetation actually helps to attenuate or stop some of this wave energy from getting to the shore. This next example I have is even more obvious, but very cool. So you could see the waves coming in. When they hit the mangroves, there's no wave on the other side. And it's because of the complexity of the vegetation and of the natural system is kind of able to do some of that wave attenuation. In that way, we can protect our shorelines without the seawalls. The nature itself is the seawall. So let me move on. So nature is the seawall. Here's a couple different examples because we talked about salt marshes. It's the top left. The mangrove forest is the same thing as another like brackish system. That's the bottom left. Then top right, we have oyster reefs, which do a lot of that work as well. And then we also have coral reefs. So kind of like no matter where you live in the world, there's like a nature-based solution suited to your coastal ecosystem. So in this way, we could protect the humans living in houses, and we could also protect the baby fish living in the marsh. And so how do we do it? How do we design these marshes? I mean, in a lot of instances, the answer is don't do anything. If the marsh is there, we got to protect the marsh. But a lot of the time, especially in cities, those ecosystems have already been destroyed. And so the question becomes, how do we rebuild these marshes back even stronger? How can we capitalize on human ingenuity to benefit all the life in the coastal zone? And so that kind of brings me to my third piece rather. This is design. So in order to do this right, we need to rethink the way we design our cities. Instead of just building over the marsh, how can we build with the marsh? Or how can we build with the oyster reef or with the mangrove forest? A lot of indigenous communities have been living with nature for thousands of years. And for some reason along the way, a lot of us humans forgot how to do that. So it's in our best interest and the best interests of our coastal community neighbors, these animals, these plants, to remember that and to innovate on that and to figure out how to do this right. So here are a couple of great examples of people already doing this work. There's living shorelines. We're thinking about, well, how can we incorporate oyster reefs into our infrastructure for our cities? How can we think about designing with water smarter? So that's basically what I've been researching here at MIT, this kind of multi-species model of coastal resilience. How we can research the way water moves through these natural systems like marshes and oyster reefs and use that to redesign our coastlines so that they're beneficial for humans and animals and plants alike. So that's kind of where we're at. I'm so excited to answer any questions anyone has.
Thank you so much, James. That was super exciting. So we already have some really, really great questions from the students in the Q&A pod, but I wanted to start you off with one. So it seems like there's a common thread through all of the things you've done. I mean, was this intentional? Did you kind of know what the next steps were going to be in your career every single time? How did that all come together?
Yeah, no, that's a great question. And I love questions like that because the truthful answer is no. I didn't really plan any of this. And I think that was kind of important in how I sort of uncovered my place within these fields. Because there's the side that's kind of like design and architecture, the side that's engineering, the side that's ecology. And I think in order for us to solve a lot of these problems that we're facing now, a lot of them are very interdisciplinary. So we need more people that are, like, oh, you were a doctor and then you became an archaeologist. Like something like that sounds crazy, but we need more people with this like sort of multifaceted perspective to solve multifaceted problems. So yeah, no, I didn't plan it, but I've kind of been going with the flow, so to speak. and I'm excited where it's brought me.
I totally love that. And that's such an enlightening answer to have, because sometimes when we're younger, we think we need to plan everything out and know every step after school and college. So it's really refreshing to hear that perspective from you, James. Now we have a question from a Nord Anglia student, and they were wondering, how do you build an oyster reef where there wasn't one before? I think you had a picture of something kind of like that.
Yeah, that's a great question. So oysters, we're used to seeing them kind of in their shell form, but that's the adult. So when they're babies, in their larval stage, they're actually planktonic. So they float around in the water column. And so when they're floating around in the water column, in order for them to get to the next stage, they latch onto a hard substrate. So a lot of the time, that's another oyster. So you see like the little baby spats, they're called, growing on adult oysters. But sometimes it's just concrete. And so what's great from a design perspective is we're sort of realizing that oysters aren't necessarily that picky about the hard substrate that it is. It could be another oyster, or it could be concrete, rocks. And so if you want to build an oyster reef, you can there's a lot of different, models or whatever, but you could put some of that hard substrate like concrete blocks or oyster shells. And then over time, the spats will attach and it'll kind of build up. So sometimes you have to start with oysters already to encourage new oysters to come. But it is kind of like a self-engineering system. And that's actually specifically my research is kind of figuring out how to do that better with the oyster reefs. So great question.
I'm glad. So James, just to follow up on that, I mean, how long does that whole process take? So you said it could take a while because the spats need to attach to things and grow from there. But, how quickly can you kind of achieve an oyster reef?
Yeah, it's not quick. And I think that's part of the issue in getting these kinds of things to catch on, because nature isn't necessarily fast. It's got no rush. It's been around for, billions of years. It's like, okay, whatever. So, the spats, it's kind of like a yearly process. You'll see growth within a year. But in order for you to get like a very mature reef, that can take years, 5 years, 10 years. And so in order for us to make this kind of infrastructure viable to like policymakers, to the politicians and the government, we need to have long-term records of how these work. Because you can't, like, I'm not going to sell this to somebody on like 1 year of oyster reef. But if I've got 10 years of oyster reef, I could say, look how well it works. So that's kind of the thing. We need more people doing it for longer to prove how well they work.
Absolutely. That makes a lot of sense. And now we have a question from Nord Anglia student with a name that I like very much. Her name is Fatma Khan. And Fatma is wondering, why do you love to study zoology?
Yeah, I think I always have just been very attached to nature. I think it comes from my mom. My mom just has always had almost like a spiritual relationship with nature and the environment. And I think she instilled that in me at a young age. So, like I said, I live in the city, but there are lots of what people call weeds, but are often just wildflowers growing in cracks in the sidewalk. And I think it's important, even if you're in a very urban area, to find that connection to nature where you can, because it is so important, not just for nature, but like I was talking about, for us as well. So, I'm the person that will stop and look at the like little wildflowers growing out of the sidewalk crack. And I think once we start doing that, we build a better relationship. So that's kind of, I really like birds. I like fish.
That's totally awesome. And it really speaks to that phrase that we hear a lot, like take some time to like stop and smell the roses and see what's around you and appreciate your environment. So that makes a lot of sense. So now we have a question from a Nord Anglia student, and they're wondering, does the shellfish industry contribute to these issues that we're having with shorelines, like erosion or, removing these natural environments for fishing purposes?
Yeah, I mean, the problem is it's never like fully yes and fully no. It depends because kind of like I said, I think there are a lot of communities historically that know how to live with the land, even if they're farming or even if they're fishing, because you can fish sustainably as long as you pay attention to not fishing too much and doing it in a certain sort of like humane is a weird word to use in this case, but in sustainable practices. So there are people in the shellfishing industry who are aware of these practices and pay attention to minimize any damage to the ecosystem. But then there are others that do not. So I think often it's a question of scale. Sometimes the really, really big ones don't pay as much attention, but I don't even think I could blanket make that statement. I think it really is like we each have the capability to pay attention to these issues. And so we're all responsible for it, no matter how big or small our corporation.
Right. And now we have a question from a Nord Anglia student, and they're wondering, how can we build salt marshes in cities that already, built on top of the old ones? Where do you decide to, start up another one?
Yeah, another complicated question because real estate, this is more from like the architecture side, real estate is often expensive. And so it's not easy to convince a real estate developer to turn this plot of land into a salt marsh because a lot of people don't yet see the benefits of salt marshes. So, I mean, from a technical standpoint, there's a lot of analysis that goes into it because we need to look at sort of the hydrology in the area. So like, what is the situation with currents in the area? What's the situation with the rain and the watershed? So there's a lot of physical analysis that goes into it. And, we could look at the soil because marshes do well in certain soils. And a lot of time urban soils have not been taken care of. So when you do a restoration project, it's a really long process of like, we've got to spend a year plus kind of doing this site analysis. But then that's just one piece, because even if you found the perfect spot for a salt marsh to do this restoration project, then the next step is like permitting and planning and getting permission from the government or whoever owns the land. So I think, it's a tricky process, but I think everyone also has some agency in the process. And so even if you don't have the capability to start like a large scale marsh restoration project, so much of this work is just getting people aware of these issues and letting people know and convincing the right people that protecting salt marshes or mangrove forests is important. And so even just sharing a post on Facebook could be instrumental.
Yeah, I'm pretty sure these amazing Nord Anglia students will definitely be spreading the word about all of the things you've discussed today after this. So we all win there. So now I think we have a question from a Nord Anglia student who I suspect will really enjoy physics class in the future. And they're wondering, and I'm going to read this question directly. So our student asks, in my country, mangroves create amazing ecosystems. From a design perspective, how do mangroves make all the messy, energetic surrounding water, get still at the end?
Yeah, so the short answer is that, when you think about a seawall, it's like totally flat and there's nowhere for the water to go. So when a wave comes, you've got this energy, it just often gets reflected right back off. So even though your shoreline behind the wall is stable, a lot of the time you've now pushed this wave somewhere else. Like you haven't actually dissipated the wave. Or worst case scenario, you deflect the wave down and then you create a scouring under the wall and now the wall might collapse. When you have a porous structure, so something with holes in it, which when you look at those mangrove roots, you can kind of see that's what they look like. It's like a holy mesh. You're doing the same thing, but because the wave is long and it's getting deflected in tiny little pieces, And there's so much like difference in the angle of those roots. You break it up in that way. So instead of one wave getting like reflected back off, half the wave gets reflected this way, half the wave gets reflected this way. And all of these reflections get like trapped within this porous field. And you know, for those of you who know about physics, we always know that we lose energy in a system. So every time there's a deflection, we lose a little bit of energy to that root or to that blade of grass. So if you have enough roots and enough blade of grass, then over time, it all gets absorbed.
Well, I can tell that it sounds like your cat really endorses that answer for sure.
Yeah. Yeah, her name is Fern.
Oh, well, I'm excited that she's with us today as well. We have a question from a Nord Anglia student who I think took notice of that really cool picture of you in the aquarium tank. And they were wondering, was the water in those tanks fresh water or salt water?
Both. So we had a couple freshwater systems. One that was based on an African rift lake. So a lot of like cichlids live in lakes like that. And then we had one that was based off of like a Southeast Asian river. So those are two freshwater systems. And then we had a local, so I was from New York City, so like a, northeastern Atlantic tank. So that was salty. We had a kelp forest tank, which was salty and very cold. Which was actually from the picture. That's why I had a hood on. And then we had a tropical reef. So also salty, but a lot warmer and a lot more enjoyable.
That makes a lot of sense. And now we have a question from a Nord Anglia student who's wondering, and I think they're referencing your zoology days and being a zookeeper. Do you have a favorite animal?
I really liked, that's so hard. Not like they understand, but I'm always like, I feel like I'm betraying someone. But I really liked, if you guys want to look up, because I had a picture of them, a tamandua is a small species of anteater. The southern tamandua, I really liked them. They're so cute.
Okay, I will definitely be Googling that immediately after this webinar. We have an amazing question from a Nord Anglia student who's wondering, you said it's in our best interest to remember how people have lived with nature for the past thousands of years. But how do we do that? Isn't that information lost?
No, it's not lost. Sometimes it's almost lost. But, well, okay, first of all, a lot of these indigenous communities are still around. It's not like ancient history. So I think a lot of what happened as sort of modern society has taken over, it's kind of suppressed the voices of a lot of different kinds of people in favor of maybe a very Western-centric sort of narrative. So a lot of those people are still here and can be sort of asked directly. But then I think even for some of the practices that we've lost, it's history, but a lot of the time it's out there. And I think it's our responsibility as educators, as well as students, to find that information, because it's definitely, a lot of it is not gone. A lot of it's just not taught in school, which is definitely a problem. So, I mean, I think the more people that talk about it, the more it gets out there, and then the more people who go to look for that information, and then, hopefully we can make some of these practices very common again.
Got it. And now we have a Nord Anglia student who's wondering, and I think they've noticed your MIT Water Summit hoodie and was really interested in the research you're doing. And they're wondering, do you think about the UN sustainability, like the Sustainable Development Goals, as part of your work? Are these things that help guide you?
Yeah, it's definitely been at MIT sort of a big push to do more research that's in line with those goals. In fact, I can't remember exactly who said it to me, but anyone who wants to be a scientist at this point has almost like a moral responsibility to be a climate scientist. And I don't mean that we all have to study the weather. I mean that like you can't do research in future technology and forget that part anymore. Like, there's no like, well, maybe if climate change wasn't a thing, this would work. No, like we all have to be, we all have to learn about this, and we all should be thinking about ways that we could mitigate some of these effects or rethink how we could live to be better resilient to different kinds of change in the future. So I think even if you're, not just science, like art, social science, it's something that we all have to be thinking about. So it's definitely on my mind for sure.
Of course, mine too, very much as someone who studies earth science. And it is true, regardless of what we study, these are problems we can think about and that affect all of us and the people we love very much.
Yeah.
We have a question from a Nord Anglia student who's wondering, what's it like to study architecture? What do you do day by day?
Yeah, so you didn't see much of it in this presentation because, I think in my program, that's a really broad question, because there are people that are very interested in sort of architectural technology, which I think is more my side of things. And then there are people who really love design and approach architecture more from an artistic perspective. So a lot of architecture school is that like ladder. It's a lot of drawing, it's building models. I have to get a tiny model up here. So I don't know, it's great studying both things at the same time, because then, in one of my classes, I'm building models and drawing things. And then in my other class, I have like mathematical problem sets. So I get a little bit of both.
Wow. So that really speaks to that integrated approach that you were talking about in your presentation. That's really cool.
For sure.
And we have a Nord Anglia student who's wondering now, could salt marshes and mangroves, help us with natural disasters like tsunamis, for example?
Yes, definitely. Because obviously, it depends. Like if you have 5 feet of salt marsh deep, is that going to stop a tsunami? No. But oftentimes these natural ecosystems are a lot bigger than that. And there's actually a lot of evidence, especially in like, I want to say Southeast Asia or maybe around India, where a lot of the mangrove forests have been deforested to put out rice fields. And so you can see like one-to-one comparison. Here's the town that has the mangrove forest still, and here's the town that does not. And the results speak for themselves. It's not like a subtle difference. And you could even see, where I'm from, we had a big storm 6 or 7 years ago, Hurricane Sandy. It might be longer than that. But again, you can see along the shore where there were like houses built right up to the beach versus where there were dunes. And the dunes are often held together because of grasses and stuff like that. And yeah, the damage difference is usually pretty stark.
Got it.
So yes, big wave action is another form of like, wave attenuation for sure.
Understood. And now we have a question from a Nord Anglia student who's wondering, did you always like design and building things and drawing? So they said, I know you always liked animals and nature, but what about like the design part?
Yeah, I mean, I did. I grew up always drawing. Actually, when I was, I used to like to draw comics. So I drew a lot of comics for myself, and then I did a little bit of, I have a minor in from my bachelor's in animation, actually. So I did like some graphic narrative design, but I realized I didn't want to do that for my career. And so I don't know, for a long time, I kind of just drew for myself. And so it was really my scuba diving instructor actually was an ex-architect. And so he started talking to me about how architecture is often this like combination of like science and art. And when he was talking to me, I was like on my way to get scuba certified. And I was like, yeah. So it felt like the art had always sort of fell by the wayside. And I'm glad I found a way to bring it back to my life.
Wow, what are the chances of that? I mean, that is totally amazing.
I know, no, it was very pivotal.
And we have a question from a Nord Anglia student in India, and they're asking, in my country, India, there are many big waves and salt marshes are not really a thing here. So how can we engineer these natural walls that are environmentally safe near our coastlines? What are the other options? Can you remind us other than salt marshes that can play a big difference?
Yeah, so that's a good point because so much of designing, like with nature is being site specific because there's never going to be a one size fits all solution. There's never going to be like here's a deployable salt marsh and I can stick it in any ecosystem and it's going to work, because you have to think about like what the local context is. So, I mean, there are the obvious things like if the climate is just not appropriate for the salt marsh, it's just not going to grow well. But then also like what other plants and animals are already there? Because when you try to apply a one size fits all solution, and when it comes to landscape design, a lot of the time you wind up introducing species that don't have any competitors, and then that's how you get invasive species problems. So I must admit, I'm not a specialist in this region, so I don't think I can speak to the specific species that are appropriate. But like I said, I do know that mangrove forests are pretty common in that area of the world, so that could be an option. But again, I think a good place to start is to see sort of like what the wild or sort of untapped context is, because oftentimes nature's already figured it out.
Hmm. Speaking of nature, having things figured out, we have a couple of Nord Anglia students who are wondering, how do the plants survive in mangroves and salt marshes having this salty water? How does that work? Because we can't drink salt water. So how do they do it?
Yeah, it's very cool. And it's cool because when you think about it, a lot of a salt marsh is what we also call a tidal marsh. So the parts near the edge of the ocean are a lot saltier than the parts near the top. So when you look at a marsh, you often see this like very obvious zonation, where there's the high marsh that has certain species that cannot tolerate a lot of salt. And then there's the low marsh that has species that can tolerate a lot. And oftentimes it's like as straight as a line. Like you can look and see that's where the tide comes up. So I know from like a sort of surface level perspective, and I don't know a lot of the technical details, but a lot of these very salt tolerant plants have special root systems that will, I think it's called, it starts with an A. I don't remember, but it actually like transfers the salt up through the plant. So they have all these like special adaptations where they're not actually like living on the salt. In fact, a lot of these plants will sweat out the salt. Yeah,
Just like we do.
Yeah, they're like the stomata. It's the same thing that opens up on the leaves and like lets in CO2 is the same, like it's the same process, like they just let the salt back out.
Wow.
So that's one example, but I know that there are a couple different adaptations for different salt tolerant species.
And we have another salt marsh and potentially mangrove related question, but you talked us through how they're able to attenuate some of that energy from those like big waves coming in. Why don't these plants get damaged? How are they able to tolerate that?
I mean, it's a combination of a lot of things. I mean, in the case of a mangrove, you see strength in the individual. But then sometimes it's not necessarily one plant being strong as it is the collection of plants being strong. Because remember, when we were talking about the wave coming in, each plant is only absorbing a little bit of that energy. If you have a huge marsh and there are thousands or hundreds of thousands or even millions of individual stalks of this, this grass, say a common one we have here is called Spartina alterniflora. So if it's one out of many, then you think about that wave energy and just chop it down into tiny little pieces. So each grass blade is a better way to say, each blade of grass is really only taking a little bit of that energy. But the other thing too, the flip side is that there is a level where they can't absorb all of the energy, right? So when you have a wall works until it doesn't. Like a wall will work, and then if we get to an amount that it just can't take anymore, it'll break.
Right.
But what's great about natural systems often is that failure is not as dramatic. So instead of it just being like one day we can hold back all the water and then one day it breaks and the floodplain is completely flooded, that failure mode is a lot more gradual. So the waves, the grasses will be able to attenuate it, and then all of a sudden the waves will be too strong and will start pushing the grasses down all the way. But it'll be like a curve as opposed to like a strict like this, which has a lot of benefits. I mean, for any of you who know like anything about building buildings, we want our buildings, if they have to fail, we want to design gradual failure so that maybe only one part falls instead of like the whole thing at the same time.
I can't help but draw analogies in my mind to teamwork versus individual in this as well, right? It seems like there's a lot of lessons from nature in that.
Absolutely. There are a lot of lessons from nature for sure.
And so, James, I wish that we could ask you all of the questions that the Nord Anglia students have asked, but I'm going to leave you with a closing question for the sake of time. So I think that some of the Nord Anglia students, based off of how amazing their questions were, really want to do what you're doing. They want to integrate engineering and sustainability and design and their love for life and animals and nature. What are some good qualities that folks who are doing what you're doing have? What are some good qualities these students can work on cultivating?
Yeah. I mean, stay inquisitive, like always ask questions. There's no such thing as a bad question. I got a lot of amazing questions today. So definitely like stay curious about your environment, what's around you, and ask questions about that. But also I think don't lock yourself in. When I was in my undergrad, I didn't know I was going to graduate and I didn't know what I was going to do because I was like, oh, I don't want to be a physicist, but I studied physics. Like, that's it for me. But that's not how it works. A lot, like I said at the beginning, a lot of our issues that we're looking at these days, and not just issues, but flipping it around and looking at it as opportunity for positive change, comes from different types of people coming to the table with different types of experiences. So just because you want to be an engineer, you don't feel like you have to give up playing the piano or, going on hikes. Like, you never know what kind of skills are going to be beneficial to you later on, or how it's going to change the way you think. That's your greatest strength. So, stay open.
Oh, that is absolutely wonderful advice, James. And unfortunately, before we go, I actually have to cue folks in to what's happening next. So I'm going to take a moment to do that. Next month, we are going to be talking about physics and poetry. So if you didn't get your physics fill today, I know I have so much stuff I want to look up and learn after this. Be sure to tune in next month to join us with McKinday, who's going to talk about how he does physics, and he's a poet. I think that's totally, totally awesome. And if you want to re-listen to any aspect of James's amazing presentation today, or you can't make it to McKinday's, be sure to check out recordings on Global Campus and as well as YouTube. And they're usually up a few days after the abstracts finish. And now I'd like to extend a huge thank you to the Nord Anglia Education MIT collaboration for making this series MIT abstracts possible. And then I also want to extend a huge thank you to James for joining us today and for spending time with us and telling us all about the amazing work he's going to do. We really can't wait to follow your future, James, and all the folks you inspire.
Thank you all so much. Thank you for having me here, and Nord Anglia and company for making this all possible. I think this is a great series.
I think so too. Well, thank you to you and your amazing cat for joining us today. And I hope you all have a wonderful rest of your day. And I'm excited to see everyone next time. Bye.